So to kick off today's deep dive, I want you to just picture this for a second. You've got your morning routine.
Oh, yeah, we all have one.
Exactly. It's a Tuesday. You haven't even had your second cup of coffee yet. And, if you're anything like Ethan, who is a veteran engineer on Microsoft's Windows networking platform team, you have very strict rules about Tuesdays.
Right, which makes sense.
Like nothing before 10 o'clock, no messaging apps before coffee, and you absolutely, under no circumstances, open the security dashboard before that second cup is totally empty.
Which, honestly, it's a necessary survival mechanism for someone in his position.
Yeah.
Yeah, I mean, when you have been in enterprise security for, 11 years, you develop this psychological callus. Because the panic-to-signal ratio on those dashboards is usually about 40-1.
That's a lot of noise.
It is. Most of these screaming, flashing red alerts turn out to be absolutely nothing. Like just a misconfigured test or, a harmless anomaly.
Right. But at 8:47 a.m., Ethan's laptop chimes, and it's a P0, a priority 0 alert. Yeah. And the notification reads, MDASH, priority finding, tcpip.sys, authentication boundary. So naturally, Ethan breaks his own rule.
He has to.
He pours the second cup first, and he opens the alert. And what he finds waiting for him isn't a false alarm. It is a critical, unauthenticated remote code execution vulnerability.
Wow.
A CVSS score of 9.8, just sitting there right at the kernel level.
Which, I mean, structurally speaking, as bad as it gets in the cybersecurity world.
Right. 9.8 is basically the ceiling.
Exactly. It means an attacker could run whatever arbitrary code they wanted on your machine from anywhere in the world without even needing a password or, any user interaction at all.
And here's the wildest part of the scenario we're unpacking today. That bug. It had been sitting there, fully exposed in tcpip.sys since 2019.
6 years.
6 straight years. It survived 4 major Windows releases. It survived countless aggressive red team exercises, extensive security audits, and thousands of hours of human review.
It was essentially hiding in plain sight.
Exactly. So today we are taking the stack of sources you sent us, and we're going on a deep dive. We've got a brand new article published just this morning, June 19th, 2026, in Tech-Reader magazine.
Great piece, by the way.
It really is. It's titled, How AI Found a Critical Windows Flaw Hidden in Plain Sight for 6 Years. And we're pairing that with Microsoft's internal architectural research on the system that actually found it, and your own notes outlining some pretty intense pushback from researchers at XBOW. So our mission today is to figure out how AI is shifting from, a simple code-writing assistant to this autonomous, argumentative security auditor.
Because we aren't just talking about a single bug in a single piece of code here.
Right.
This collection of sources, it outlines a monumental shift in how we secure our entire digital infrastructure. I mean, we're looking at an AI system that doesn't just read code passively, it actively debates with itself to find the truth.
Which is mind-blowing. But let's start with the bug itself. Because if we want to understand how a machine finally found this hidden nightmare, we first have to understand why human experts, literally some of the best network engineers on the planet, why they missed it for 6 straight years.
Yeah, and it fundamentally comes down to the nature of the vulnerability.
Yeah.
When we think of coding errors, we often imagine, rookie mistakes, right?
Like a typo or something.
Right. We think of a typo or a classic buffer overflow or maybe a hard-coded password that was just accidentally left in a text file.
Sure.
But this was none of those things. It
Yeah.
wouldn't even show up in a standard static analysis scan. This was a highly complex race condition.
Okay, so for those of us listening who aren't kernel engineers, what exactly does a race condition look like in this context?
Well, mechanically, a race condition happens when a system's behavior depends on the sequence or the timing of other uncontrollable events.
Okay.
So in this specific case, the race was between 2 completely different, highly complex subsystems within the network stack. On one side, you have the TCP state machine, and its job is to handle the incredibly complex, rapid-fire transitions of network connections, opening ports, acknowledging packets, closing connections, that sort of thing.
Got it.
And on the other side, you have the authentication token validator, which is responsible for ensuring the user or the process have the right permissions to actually perform those actions.
Okay, so let me try an analogy. Think of it like 2 perfectly run train lines in a massive city.
I like this, yeah.
So train line A, the TCP state machine, runs on its own rigid schedule. Train lane B, the authentication validator, runs on its schedule. They are both engineered flawlessly in isolation.
Completely flawless.
But no one realized that under one incredibly specific, bizarre condition, they cross the exact same intersection at the exact same millisecond. Each system is operating flawlessly right up until they inevitably collide.
That is a brilliant way to visualize it. And in the Tech Reader article, Brooke, who is the team's security architect, she coined a specific term for this. She called it a layered assumption failure.
Layered assumption failure.
Right, because the bug didn't actually exist in the code of either subsystem. It existed in the invisible gap between them.
The blind spot.
Exactly. The developers assumed that a particular token validation would always mathematically finish before a specific network home transition occurred. And, 99.99% of the time, in the real world under normal network loads, that assumption held up perfectly.
But if an attacker knows exactly where that intersection is and exactly how to manipulate the timing of the network traffic to force both trains into the crossing at the exact same time, boom.
Boom.
They break the assumption, bypass the token validator, and gain kernel-level access.
Precisely. And this highlights exactly why human reviewers missed it for over half a decade. I mean, to find this vulnerability organically, a human engineer would have to hold the intricate millisecond timing dependencies of both subsystems in their head at the exact same time.
That sounds impossible.
And then they would have to mentally simulate what happens when those dependencies fail under duress.
In a code base that is, 200,000 lines long?
That is the crux of the issue right there. Holding 200,000 lines of code in your working memory, it isn't a matter of human intelligence or engineering skill. It's a completely impossible issue of scale.
Right, our brains just aren't built for that.
No, the human brain relies on cognitive shortcuts to function. We recognize patterns, we look at a block of code and say, oh, I've seen the structure before, it looks fine. But that necessary evolutionary bias blinds us to the unfamiliar chaotic gaps between these massive systems.
So if human working memory caps out at holding a few hundred lines of code at a time, how do you reliably audit 200,000?
You don't. At least not manually.
Right. You can't just throw more human engineers at the problem because their cognitive blind spots will just overlap.
Exactly.
So you need the system that possesses both an encyclopedic memory of the entire code base and the deductive reasoning to spot a collision in the dark. And that brings us to the architecture that finally cracked it. Let's talk about MDASH.
Yes, MDASH. It stands for Multi-Model Agentic Scanning Harness. And the first, most vital distinction Microsoft makes in their underlying research is that MDASH is not just a massive AI model.
Right, so it's not like Ethan is just copying and pasting 200,000 lines of kernel code into a standard chatbot prompt and asking, hey, can you find the bugs in this?
Oh, far from it. That approach would be absolutely disastrous.
Yeah, I'd imagine.
MDASH is an orchestration harness. Think of it as a highly structured, automated assembly line utilizing more than 100 specialized AI agents, all working in a synchronized sequence across an ensemble of different models.
Okay.
The AI models themselves are merely the raw computational engines.
Yeah.
The architecture of the harness, how it directs those engines, that is the actual product.
Well, let me pause you there and push back on behalf of the listener for a second, because anyone who has used modern AI has seen it confidently give completely wrong answers.
Oh, absolutely.
Right. It hallucinates facts. It makes up code libraries that just don't exist. So how on earth can a massive enterprise trust a generative AI system to hunt for critical kernel vulnerabilities? I mean, if Ethan already has a panic-to-signal ratio of 40-1, wouldn't a hallucinating AI just drown the engineering team in an ocean of false positives?
That skepticism is entirely justified, and it is exactly the structural problem MDFH was built to solve. The system is fundamentally designed around the assumption that raw AI models will hallucinate and they will generate false positives.
Oh, so they just expect it to mess up.
Yes. To combat this, MDAH doesn't just spit out guesses. It forces every potential finding through this brutal, rigorous 6-stage pipeline to systematically filter out all that noise.
Walk us through that pipeline then, because the way the Tech Reader article describes this process, it feels like we're looking at the blueprint for a digital immune system. How does it start?
Well, it starts with the prepare stage.
Yeah.
Before MDAH even begins hunting for vulnerabilities, it has to build a comprehensive context of the environment. It doesn't rely on what the human-written documentation claims the system does. It maps what the compiled code actually does in reality. It builds a working map of call graphs, analyzes memory allocation patterns, and traces privilege boundaries across the entire architecture.
So it builds an undeniable map of the actual territory.
Exactly.
And once that scaffolding is in place, we move to the scan stage. And this is where the sheer computing scale really comes in, right?
Yes, this is where the orchestration harness deploys a massive fleet of specialized AI agents to fan out across the code base in parallel. And their specialization is key here.
What do you mean by specialization?
Well, MDASH just doesn't use generalist agents. One agent might be strictly programmed to only look for integer overflows in memory allocation. Another agent only looks for timing assumption violations.
Oh, wow.
Yeah. They cast a massive parallel net, and unlike human engineers, they never experience alert fatigue. They never develop that, I've seen this before, cognitive bias.
But, casting a massive net means catching a lot of garbage along with the fish. Which brings us right back to my concern about false positives. If an agent finds a theoretical integer overflow, how does it know if it actually matters?
And that requires the validate stage. Standard older static analysis tools are notorious for throwing these bright red flags for code paths that are theoretically flawed, but literally impossible to reach in a real-world execution.
Right, which is just annoying for the developer.
It's extremely annoying.
Yeah.
So the validation agents in MDASH have a single distinct job. They look at a flagged finding and ask, is this pathway actually reachable under real conditions?
Meaning
Meaning they check if a firewall rule, a privilege requirement, or a hardware limitation would block the path. If the pathway isn't reachable, the finding dies right there.
Okay, but here's the stage that completely blew my mind in the research notes, the debate stage.
Oh, yeah.
The article calls this the ultimate game changer. Mechanically, how does a machine debate with itself? Is it just running the same prompt twice and comparing the output?
It is much more adversarial than that. Once a finding survives validation, the orchestration harness deploys a completely separate set of adversarial agents. You can think of them as defense lawyers.
Defense lawyers. Okay.
Yeah, their sole directive is to dismantle the prosecution's case. They are actively trying to kill the finding.
So instead of trying to prove the bug exists, they are trying to prove it's a ghost.
Precisely. They will examine the proposed exploit path and actively search the surrounding architecture for mitigating controls. They will argue that the vulnerability isn't exploitable in practice. They might even generate countercode to demonstrate that a required memory condition is impossible to assemble simultaneously.
That is wild.
Right. The original finding has to survive this intense automated cross-examination. If the initial agent cannot successfully defend its finding against the adversarial agent's logic, the alert is dropped. It never reaches a human.
But wait, let me throw another wrench in this. If you have 100 specialized agents fanning out in parallel, scanning a massive code base, aren't they inevitably going to stumble over the same bug from slightly different angles?
Oh, definitely.
Like, Agent A finds the memory leak, Agent B finds the timing error, but they're both caused by the exact same intersection collision. If Ethan gets 50 PIV alerts for the same root issue, the system has still failed, right?
That is a brilliant observation, and it highlights the necessity of the deduplication stage. MDAH anticipates that overlap.
How so?
It utilizes another layer of agents to analyze all the surviving debated findings and trace them back to their root origins. It collapses all the different attack vectors and angles into one single, clean root cause report.
Which culminates in the final and undoubtedly most crucial stage of the pipeline. Prove.
Yes.
Yeah.
The fundamental rule of MDASH is that it does not deliver a hypothesis to the human engineer.
Right.
It does not say, hey, this section looks suspicious, you should check it out. It delivers a 100% verified, mathematically sound case.
So when Ethan opened his dashboard on that Tuesday morning, he wasn't looking at a guess. MDASH handed him a fully mapped exploit path traversing 847 lines of code.
847 lines. Just incredible.
It showed the exact sequence of concurrent operations required, the specific boundary violation, and the resulting privilege escalation. It essentially handed the engineering team a flawless blueprint of exactly how to hack their own system.
Which is terrifying when you think about the implications, but incredibly valuable from a defensive standpoint. Because, what is the human reaction when an artificial intelligence drops a fully weaponized zero-day kernel exploit into an engineer's lap right before morning stand-up?
I would imagine the initial reaction involves a lot of panic and probably spilled coffee.
Highly controlled panic, perhaps. The article notes that Ethan immediately called Brooke, the security architect, and this detail is vital. Even with MDASH providing the exact verified map of the exploit, it still took Brooke 40 minutes of intense manual review to trace the route through the TCP state machine and confirm the timing dependencies.
Wait, it took one of the best security architects in the world 40 minutes just to verify a map she was already holding in her hands?
Yes.
That really drives home how utterly impossible it would be for a human to find that collision from scratch in the dark.
Exactly.
But because Ethan and Brooke started from a place of absolute certainty rather than a vague, unverified hypothesis, the team moved with unprecedented speed. They had a functional patch written by Thursday. It cleared internal review and testing by Monday.
And this timeline raises a critical point about how the tech industry views the life cycle of a vulnerability. Fixing complex architectural bugs is often just as difficult and time-consuming as finding them in the first place.
Sure, because you could break something else.
Right. Understanding the broken interactions well enough to patch them without accidentally breaking another critical system in the process requires deep systemic knowledge. Because MDASH provided the exact root cause and the specific timing dependency, the engineering team completely skips the days or even weeks usually spent trying to reproduce the issue in a lab environment.
It represents a massive paradigm shift in software development. The article quotes David, a security architecture lead, who articulates this beautifully. He talks about how security has historically been treated as a gate.
Yes, a gate.
You write the code, you attempt to compile it, and then hit the security checkpoint where you wait for a human review.
Yeah.
It creates massive backlogs. Engineers get frustrated by the bottleneck and actively look for workarounds just to ship their product on time.
But when you integrate a system like MDASH to run autonomously on every single code commit, continuous inspection becomes a core part of the infrastructure. Security stops being a rigid, frustrating gate and becomes a fluid environment.
Right.
The code is essentially breathing security. It is always being read, always being mapped, and constantly being debated by these adversarial agents.
And the proof that this environmental approach actually works is right there in the benchmark data. The article mentions a grueling internal security benchmark called CyberGym. When MDASH first launched, it scored an 88.45% capture rate, which is great. But in under 3 weeks, that score jumped to a staggering 96.55%.
As a massive leap.
Huge. And the critical takeaway from the research notes is that this massive leap in performance did not happen because the underlying AI models suddenly got smarter.
Exactly. They didn't plug in a radically new frontier model with a higher IQ. The improvement came entirely because the orchestration harness itself got better.
Oh, interesting.
Yeah, the engineers refined the adversarial debate logic. They tightened the deduplication process to catch more overlapping angles. They added more specialized agents to the scanning fleet.
So it's the structure, not the engine.
Right. The system is learning and improving at the architectural pipeline level. If you upgrade the raw AI model, you might get, incremental linear gains. But when you improve the harness that controls the models, you achieve structural exponential leaps in performance.
So we have this incredible, quantifiable success story. The impossible bugs are getting squashed, the benchmark scores are flying up, and Ethan is finally getting some peace of mind on Tuesday mornings.
Finally.
But of course, in the hyper-competitive, fast-moving world of artificial intelligence, there is always a fierce counterargument. Not everyone agrees that this heavy, highly structured pipeline is the permanent future of AI security.
That is true. Your notes highlight the perspective of researchers at a prominent AI firm called XBOW.
Yeah.
And their fundamental perspective is that rigid multi-stage pipelines like MDASH might actually end up constraining newer, vastly smarter frontier models.
Okay, let me make sure I'm wrapping my head around their philosophy here. The XBOW argument is essentially that keeping this intense multi-stage harness wrapped around an AI is like putting heavy training wheels on a high-performance racing motorcycle.
I like that analogy.
Right. It makes perfect sense when the writer, or in this case the older AI model, is a bit wobbly and prone to hallucinations. But eventually, as the motorcycle gets faster and more capable, those training wheels are just going to create drag and slow the bike down.
That perfectly encapsulates their core argument. The XBOW researchers view the orchestration harness as temporary scaffolding.
Temporary scaffolding.
Right. It was scaffolding built for older generation models that fundamentally lacked the raw native intelligence to trace complex vulnerability chains independently. They worry that as frontier models become exponentially more capable of holding vast amounts of context simultaneously, forcing them to pause and run through fixed sequential debate stages will simply be an inefficient waste of compute power.
So what does this mean for Microsoft's approach? Do they accept that premise? Like, do they plan to just take the training wheels off once the underlying models hit a certain threshold of intelligence?
No, Microsoft pushes back on that premise entirely. Their defense of the MDASH architecture is deeply rooted in the concept of adversarial discipline.
Adversarial discipline.
Yes, they argue that even a highly capable, incredibly smart raw model will inevitably produce false positives if it isn't structurally forced to challenge its own assumptions.
Ah, I see the parallel here. It doesn't matter how brilliant the AI is. If it doesn't have a defense lawyer actively built into its cognitive process, it is going to make lazy assumptions.
Exactly.
Just like the brilliant human developers made lazy assumptions about the TCP state machine and the token validator never crossing paths.
Precisely the point. The harness isn't a set of training wheels for a weak model. It is rigorous, necessary quality control for any model, regardless of its baseline intelligence. Microsoft argues that raw intelligence alone does not guarantee accuracy, especially at the scale of global enterprise architecture.
Makes sense.
The debate and proof pipeline is what provides the necessary adversarial friction to ensure truth. I mean, you don't fire your entire quality assurance department just because you hired a really brilliant lead engineer.
Wow, that makes total logical sense. The theoretical debate over the best approach will certainly continue to rage in the research papers, but as the Tech Reader article points out, while the researchers argue over theory, the critical vulnerabilities in the real world keep getting patched.
The results speak for themselves.
They really do. Which brings us right back to Ethan. The article notes that for weeks after that critical patch shipped out to the world, Ethan kept a printed copy of that original MDASH finding sitting right on his physical desktop.
Yeah, that stood out to me.
And he didn't keep it there as a trophy of a battle won. He kept it as a sobering reminder.
Because he realized the absolute limits of his own perception.
Exactly. 3 years prior to this event, during a completely different, highly rigorous security sweep, Ethan had personally reviewed that exact section of tcpip.isis.
He had his eyes right on it.
Right on it. He had read the code carefully, he had traced the logic, and he found absolutely nothing. He didn't know what to look for, simply because the search space of the intersection was too vast for any human mind to hold at once. He was looking for a needle, but he didn't even realize he was standing in the wrong haystack.
The complexity had outgrown human cognition.
And that is the massive takeaway for you listening right now. Thanks to this deep dive into the architecture of MDAH, hundreds of millions of machines running the Windows networking stack are fundamentally safer today than they were the week before Ethan's Tuesday morning alert. The vulnerability waited silently for 6 years. And an artificial intelligence, locked in a rigorous debate with itself, finally dragged it into the light.
You know, if we pull back and connect this localized event to the broader trajectory of technology, it leaves us with a deeply profound question to consider regarding our relationship with the systems we build.
I'd love to hear it.
If AI is now strictly required to find the hidden flaws in code written by humans, because the sheer complexity of that code has officially surpassed our cognitive limits, what happens when AI begins writing entire enterprise architectures itself?
Oh, wow.
Are we rapidly approaching an era where our digital infrastructure is so incredibly complex, so densely layered with interconnected assumptions, that humans are permanently managed out of the loop of understanding it? Will we inevitably reach a point where we rely entirely on machines to audit other machines simply because the scale of the intersection is completely invisible to the human mind?